All right, ladies and gentlemen, so I am going to do the lesson on galaxies and HR diagrams really quick, just in case I lose power or something. All right, so galaxies are on review book pages 40 to 44 if you're following along. There are many different shapes and sizes of galaxies. Ours, specifically in the Milky Way galaxy, is a spiral galaxy. So what is a galaxy? It's just basically a collection of millions or billions of stars. Right? We don't know if there's other solar systems, but we're assuming that there are. Right? Here are the different shapes that it could be. They could be spiral, they could be elliptical, they could be spherical, or they could just be some random irregular shape. The sun is a part of the Milky Way galaxy, which is a spiral galaxy. That's our galaxy. The sun is the middle of our solar system, but the sun is not the middle of our Milky Way galaxy. Make sure you understand that. We are not a part of the middle of the Milky Way galaxy. We're located on one of the spiral arms. That center is known as a galactic center. Okay, we are not even close to that. All right, so in order of size, galaxy, solar system, or universe. Well, the universe is going to be the largest, then comes the galaxy, then comes the solar system. Okay, so it goes in that order. All right. So which sequence correctly lists the relative sizes from smallest to largest? Well, we know from the smallest, it's going to be our solar system. So 3 and 4 are out. Then it should be the universe. Then it should be the Milky Way galaxy because the Milky Way galaxy and then the universe because it goes solar system, which is a part of the galaxy, which is a part of the universe in general. Okay. So there's this thing called the Hertzsprung-Russell diagram. On your reference table, it's also the page 15 where it says the characteristics of stars is one we were talking about yesterday, right? It graphs the stars in comparison to our sun. So this is going to compare how bright they are, or the luminosity, and the temperature, which is going to give me the color. Okay. So on that diagram, those are the two things that they're categorized as, either the temperature and the luminosity. And again, it all has to do with how they are in comparison to our sun, because you have to compare it to something you know. So the sun is going to be that middle property. Okay, so these are the types of stars listed on the HR diagram. We have the main sequence. All right, that's the band into which most stars will form. If you look at the HR diagram, that's the thickest band. Okay. This means they have high temperature and high luminosity, right? Because if you look at it, that's what it says on there, right? And then it goes to low temperature to low luminosity. So it spans the entire chart, right? Then you have red giants and supergiants. Red is one of those colors that are cooler, okay? But giants and supergiants are very, very, very large stars. Okay, they are very luminous because they are up higher on the chart, okay, and they are very large. Right, then you have white dwarfs. White is going to be one of those colors that is extremely hot, okay, but if you look, they are also down at the bottom left-hand corner of the chart themselves, okay. So here's the chart. Here's the main sequence right here, okay. We have white dwarfs over here. We have supergiants and giants. Now, you can have blue supergiants and blue giants, okay? It's just a matter of where they are, all right? Notice that the sun is right here in the middle, and we're basing the luminosity and the temperature off of that, all right? These are all the different names of some popular ones that you're going to need to know how to identify on the region. So we have Betelgeuse, which is up here. We have Rigel, which is here, Pollux, Alpha Centauri, and Proxima Centauri, which is the star that is closest to Earth. Okay. So, on Earth Science Reference Table, page 15, you're going to shade the charts where all of the stars are hotter than their sun, and then you're going to draw a line on the chart which separates those stars brighter than our sun and those less bright. That's an activity we would do in class, but just in case. So a star's color is going to depend upon the surface temperature, okay? As they get hotter, they go from red all the way down to blue. when you are looking at this chart, okay, something to keep in mind. The hottest temperature is not all the way to the right. The hottest temperature is all the way to the left. Okay, so keep that in mind. 30,000 Kelvin, between 30,000 Kelvin and 20,000 Kelvin, you'll have like a blue star. When you have a red star, it's all the way between 2,000 and 3,000 Kelvin. Okay, so that's the coolest, and blue is the hottest. Okay. Let's talk about that HR diagram. I love this picture better because it does give you the sizes of the stars. It gives you the the colors of the stars, so it's showing you also how hot they are. And again, you can see that you can have blue supergiants, which are very large. You can have yellow supergiants. You can have red supergiants, which are colder, but they're still larger. Okay. If I were you, I would take a picture of this and put it in your notes just so that you have it so you can visually see it. You can also have blue dwarfs, which are extremely hot but extremely small, and red dwarfs down here, which again are very cold, but they're also very small. Okay, so what are the main classifications of the stars? Well, we have the main ones that we see a lot of times are blue supergiants, red giants, main sequence, white dwarfs, and red dwarfs. Those are the main ones that we see. That does not mean that there aren't blue dwarfs or red supergiants or blue giants, okay? But these are the main ones that we see. Okay, so what type of star is our sun classified as? So when you look at the chart, right, it's in that main sequence. So our sun is a main sequence star, all right, because that's where it is located on the chart itself. All right, what color are the stars in the constellation Orion? Well, to know that, you need to know what stars are in the constellation Orion. Okay, that is Betelgeuse and Rigel. Okay, according to the HR diagram, or the star classification of stars diagram, what you should do is pause it, go figure it out, and then come back. Okay, so Betelgeuse ends up being red, and Rigel ends up being blue. Okay, it's just reading the chart. That's one of the skills you're going to have to know how to use. All right, so which statement describes a general relationship between the temperature and luminosity of a main sequence star? All right, well, if the temperature is decreasing, you're down here in the bottom right, which means that the luminosity is also going to decrease. If the temperature is increasing, you're up here in the top left, which means that the luminosity is always going to increase. So therefore, it's a direct relationship. You have to pick the one that says a direct relationship. Okay, compared to other groups of stars, the group that has relatively low luminosities and relatively low temperatures is. Again, you should be looking at the chart. If it's a relatively low luminosity, we're down at the bottom. And if it's a relatively low temperature, be careful of this, it's all the way to the right. So the right side is red, and it's also the smallest one. So the answer should be red dwarfs. Okay, hopefully you guys are pausing this in between and trying to figure them out for yourself. So which list shows stars in order of increasing temperature? The hint for this is find each star and write down what their temperature is. So you'd find Barnard star, Polaris, Sirius, Rigel, Aldebaran, Procyon B, okay, and then compare them. When you compare them, you find out that the first one is the answer. Now, again, you're doing this on your own and pausing it in between. All right. So we said before that the stars are born, they live, they die. Right. So stars are born in a cloud of gas called the nebula. You saw the nebula theory the other day when we were talking about the asteroid belt. Okay. So it's pretty much the same idea as when our solar system was born. All right. So most of the stars are going to remain in that main sequence, all right, until all of their hydrogen has been completely changed to helium or gone away or changed to something else, okay? Once that happens, they will go, depending on its size, they will either become a white dwarf or a neutron star, pulsar, or black hole. So it depends on which way they're going. So if you're an average sized star like our sun, eventually when it goes through the red giant phase, once it depletes all of its hydrogen, it will become a white dwarf. Okay, a larger star, so anything bigger than our sun, are becoming a supergiant eventually, and then it's going to explode as a supernova. And then the result of that is going to be either a neutron star, a pulsar, or a black hole. So it's either, if you're an average star or smaller, you go to a white dwarf, or a large star will go to a neutron star, black hole, or a pulsar. Okay, know this picture. This picture is on Earth Science Reference Table, page 43. If you want to take a picture of it right now, and I suggest you do that and put that into your notes, because this one's got all the excuse me, it's got all the colors, so you can really see it. So you start off with the cloud, right? Let's say it ends up with an average star. That average star will eventually become a red giant. That red giant will become a different planetary nebula and eventually become a white dwarf. Okay? If you come out of the nebula and you are a massive, a very large star, you're going to eventually become a red supergiant. So notice how they do both cool down. Okay? You have this supernova event, and it either turns into a neutron star or a black hole. Every year, kids ask me about black holes, so here's a video on it.
Commercial. You could take your ulcerative colitis treatment in a different direction. Talk to your...
Black holes are one of the strangest things in existence. They don't seem to make any sense at all. Where do they come from? And what happens if you fall into one? Stars are incredibly massive collections of mostly hydrogen atoms that collapse from enormous gas clouds under their own gravity. In their core, nuclear fusion crushes hydrogen atoms into helium, releasing a tremendous amount of energy. This energy, in the form of radiation, pushes against gravity, maintaining a delicate balance between the two forces. As long as there is fusion in the core, a star remains stable enough. But for stars with way more mass than our own sun, the heat and pressure at the core allow them to fuse heavier elements until they reach iron. Unlike all the elements that went before, the fusion process that creates iron doesn't generate any energy. Iron builds up at the center of the star until it reaches a critical amount, and the balance between radiation and gravity is suddenly broken. The core collapses. Within a fraction of a second, the star implodes, moving at about a quarter of the speed of light, feeding even more mass into the core. It's at this very moment that all the heavier elements in the universe are created as the star dies in a supernova explosion. This produces either a neutron star, or if the star is massive enough, the entire mass of the core collapses into a black hole. If you looked at a black hole, what you'd really be seeing is the event horizon. Anything that crosses the event horizon needs to be traveling faster than the speed of light to escape. In other words, it's impossible. So we just see a black sphere reflecting nothing. But if the event horizon is the black part, what is the whole part of the black hole? The singularity. We're not sure what it is exactly. A singularity may be infinitely dense, meaning all its mass is concentrated into a single point in space with no surface or volume, or something completely different. Right now, we just don't know. It's like a dividing by zero error. By the way, black holes do not suck things up like a vacuum cleaner. If we were to swap the sun for an equally massive black hole, nothing much would change for Earth, except that we would freeze to death, of course. What would happen to you if you fell into a black hole? The experience of time is different around black holes. From the outside, you seem to slow down as you approach the event horizon, so time passes slower for you. At some point, you would appear to freeze in time, slowly turn red, and disappear. While from your perspective, you can watch the rest of the universe in fast forward, kind of like seeing into the future. Right now, we don't know what happens next, but we think it could be one of two things. One, you die a quick death. A black hole curves space so much that once you cross the event horizon, there is only one possible direction. You can take this literally. Inside the event horizon, you can only go in one direction. It's like being in a really tight alley that closes behind you after each step. The mass of a black hole is so concentrated, at some point even tiny distances of a few centimeters would mean that gravity acts with millions of times more force on different parts of your body. Your cells get torn apart as your body stretches more and more until you're a hot stream of plasma, one atom wide. 2. You die a very quick death. Very soon after you cross the event horizon, you would hit a firewall and be terminated in an instant. Neither of these options are particularly pleasant. How soon you would die depends on the mass of the black hole. A smaller black hole would kill you before you even entered its event horizon, while you probably could travel inside a supermassive black hole for quite a while. As a rule of thumb, the further away from the singularity you are, the longer you live. Black holes come in different sizes. There are stellar mass black holes with a few times the mass of the Sun and the diameter of an asteroid. And then there are these supermassive black holes which are found at the heart of every galaxy and have been feeding for billions of years. Currently, the largest supermassive black hole known is S50014 plus 81, 40 billion times the mass of our Sun. It is 236.7 billion kilometers in diameter, which is 47 times the distance from the Sun to Pluto. As powerful as black holes are, they will eventually evaporate through a process called Hawking radiation. To understand how this works, we have to look at empty space. Empty space is not really empty, but filled with virtual particles popping into existence and annihilating each other again. When this happens right on the edge of a black hole, one of the virtual particles will be drawn into the black hole, and the other will escape and become a real particle. So the black hole is losing energy. This happens incredibly slowly at first, and gets faster as the black hole becomes smaller. When it arrives at the mass of a large asteroid, it's radiating at room temperature. When it has the mass of a mountain, it radiates with about the heat of our Sun, and in the last second of its life, the black hole radiates away with the energy of billions of nuclear bombs in a huge explosion. But this process is incredibly slow. The biggest black holes we know might take up to a good old years to evaporate. This is so long that when the last black hole radiates away, nobody will be around to witness it. The universe will have become uninhabitable long before then. This is not the end of our story. There are loads more interesting ideas about black holes. We'll explore them in part 2.
So that's pretty much what you need to know about black holes. Here's another picture of all the different sizes. Look at the life cycle of our Sun, right? We are right here. So we have a bunch of time until the end of the life cycle of our Sun. So that is the end of that. I shouldn't have done that. And I will be posting this for you guys, hopefully in a little while. Okay, have a good one.